the antiderivative theorem. So, let f be a continuous function on a region G, okay, then the following statements are equivalent. Okay. And the statements are: 1, f has an antiderivative capital F throughout the region G. Okay. What that means is that, i.e., there is a function capital F, okay, defined on all of G, such that capital F is analytic at every point in G, okay, analytic on G, and the derivative of f is little f of z for all z, for any z in G. Okay, that is what having an antiderivative means. Okay. So, this statement is equivalent to the following second statement, that the contour integral of f of z dz is equal to 0 on any contour gamma which is closed. Okay. So, for every closed contour gamma, okay, which is completely contained in G. Okay. So, gamma should be in G. Okay. So, the first statement is equivalent to the second statement, which in turn is equivalent to the following third statement. Let A be a point in G and let B be another point in G. Okay. So, then the contour integral of f of z dz over gamma, okay, is a constant, okay, for any gamma lying in G with initial point A and final point B. Okay, what that means is that if A is the initial point and B is the initial point of the contour gamma, then it does not matter how gamma travels in G. So, in other words, the contour integral is called path independent. Okay. So, the contour integral of f only depends on the endpoints A and B. Okay. So, this statement is equivalent to 1 and 2. Okay. So, that is the assertion of this theorem. So, let us see a proof of this. Okay. So, you will immediately recall the fundamental theorem of calculus, the complex version, which we have proved earlier. Okay. It immediately gives you that the first statement, that there exists an antiderivative, immediately gives you 2 and 3. Okay. So, 1 implies 2 or 1 implies 3 due to the fundamental theorem of calculus. Okay. So, let me write the fundamental theorem of calculus, the complex version, of course, the relevant version, complex version. Okay. So, right, because if little f were the derivative of an analytic function, then the integration on closed contours we proved will be 0, and and we also proved that the integration, line integral, will depend only on the endpoints. Okay. So, the value in part 3 of the line integral will be the value of the function capital F at the point B minus the value of the function capital F at the point A. Okay, so, this we did earlier. Okay. So, now we need to well, there are various ways we can prove this equivalence of these three statements. What we will do is we will prove that 2 implies 3. Okay. So, proof of this once again is very easy. The proof that 2 implies 3 also follows very immediately. Okay. What you can do is let gamma 1 and gamma 2 be 2 paths or 2 contours, okay, with initial point A and final point B. Okay. So, we will take any 2 contours, okay, with initial point A and final point B, okay, and let gamma 1, gamma 2 lie in G. So, we will allow them, we will make sure that they lie in G and their initial point is A and the final point is B. Then what we want to show is that the line integral of f on gamma 1 is equal to the line integral on gamma 2 by assuming that 2 is true. We are trying to prove that 2 implies 3, right. So, we will assume 2 is true. Okay. So, then gamma 1 minus gamma 2 is going to be a closed contour, is a closed contour. Recall what minus gamma 2 means, okay. You trace gamma 2 in the opposite direction. Okay. So, gamma 2 is a closed contour with initial and final points A. Okay. Initial and final point will be A itself. Okay. So, that 2 tells us by 2 we are assuming 2. So, by 2 the integral, the line integral f of z dz on the contour gamma 1 minus gamma 2 is 0. Okay. So, by properties of line integral, the left hand side is f of z dz on gamma 1 minus the line integral on gamma 2 of f of z dz is equal to 0. Okay. So, 3 is true. Okay. 3 is true. So, that tells that the contour integral does not depend on the path from A to B. Okay. So, so that is your proof of 2 implies 3, that is very easy. Okay. So, the more difficult part of this theorem is to prove that we will prove proof of 3 implies 1. So, we will try to show that statement 3 that the contour integral is path independent will imply that there is an antiderivative for the function, for the continuous function little f. Okay. So, in order to prove this, well, we will construct a function, okay, and then we will show that that is analytic. Okay. So, suppose f of z dz, the line integral of that on gamma depends only on the initial point and final points of gamma, that is we are assuming 3, okay, for any gamma that lies in G, lies in the region G. Okay. So, now fix a point z naught belongs to G. Okay. You fix a point and define capital F of z to be the integration over gamma of f of z dz, where gamma is any, okay, contour, okay, in G, which lies completely in G, okay, from Z naught to Z, okay, where okay. So, this Z should belong to G, of course. So, fix Z naught belongs to G, let Z belong to G. Z is a point in G, okay. So, define capital F of Z to be that. Okay. Firstly, some notes here. F is well defined because of our assumption. It does not matter which contour you pick, gamma is any contour in G, but capital F is well defined, okay, because we are assuming 3 here. Okay. So, F is well defined since 3 is assumed, statement 3 is assumed, that is this is path independent, the contour integral is path independent. Okay. That is the first note. Okay. And then the next is we will introduce a notation. We will say this we will write integral over gamma of f of z dz as as we will write this as integration from z naught to z f of z dz. Okay. What that means is we do not care about which path we take from z naught to z, as long as that path lies in G. Okay. So, you take the contour integral from z naught to z, okay, and that this notation on the right hand side means that you take this. Okay. So, with this we will rewrite the definition of f of z. F of z is the contour integral from z naught to z of f of z dz. Okay. So, the only catch here is that you should make sure that the path from z naught to z or the contour from z naught to z lies within G. Okay. All right. So, with that agreement we will introduce this notation. Okay. So, we want to show that f is analytic, this function. So, we have constructed a function. Now, we want to show that is analytic. First, let us estimate or let us see what the modulus of f of z plus h minus f of z by h minus f of z is. Okay. We are doing this estimate because we suspect that f prime, capital F prime of z is going to be little f of z. Okay. So, we first take a z belongs to G, okay, and consider modulus of f of z plus h minus f of z by h minus little f of z. Okay. So, this is going to be by definition of capital F, this is the integration, this is the line integral from z naught to z plus h of f of, I need a different variable here, zeta d zeta, okay, minus the line integral from z naught to z of f of zeta d zeta, okay, that is your definition of capital F of z plus h and capital F of z, okay, divided by h minus f of z. Okay. So, once again we will assume that the contours from z naught to z plus h and z naught to z lie in G. So, here is a schematic picture. Okay. So, here is your region G, this is the region G, okay, and z naught is a fixed point, okay, and your z is here, and we want z plus h. Eventually, we are going to let z plus h be very close to z. Okay. So, then you take any contour from z naught to z and some other contour from z naught to z plus h, okay, and then okay, and then you are looking at the difference of these line integrals in the estimate. Okay. So, it is clear from this expression here, that this is the same as going back on this path, okay, and then coming back along this path will give you the path from z to z plus h, or a path from z to z plus h. Okay. So, the above estimate, okay, the above estimate is equal to the integration from z to z plus h of f of zeta d zeta by h minus f of z. Okay. We are able to do this because the line integrals are path independent in G. Okay. The line integrals of little f are path independent, otherwise we will not be able to go from that step to this step which I have just written. Okay. So, using this what we can say is that, well, since G is open and Z is a point in G, what we can do is you can find a small ball around Z completely contained in G. Okay. So, we will say that a delta ball lies in G. Okay. So, there is a delta positive, okay, let me call that delta naught positive, such that B Z delta naught, a ball of radius delta naught, an open ball of radius delta naught centered at Z is contained in G. Okay. So, when the modulus of h is less than delta naught by 2, okay, the straight line joining z and z plus h, okay, is contained in G. Okay. So, here in this estimate, okay, we do not care what path we take from z to z plus h. Okay, here is z and here is z plus h. So, let me go back to the above picture. We do not care what path we take from z to z plus h. We are interested in the contour integral of f, okay, along any path from z to z plus h. So, what we are, since G is open, okay, when you consider h to be small enough like this, okay, the straight line from z to z plus h, okay, is of course contained completely within G. So, that we can pick, okay, so pick the straight line path or straight line contour from z to z plus h, okay, for the above integral when modulus of h is less than delta naught by 2. Okay. So, then this estimate we were making f of z plus h minus f of z by h minus little f of z, okay, this estimate is going to be your modulus from z to z plus h. Now, I need a notation for straight line path. Let me say z comma z plus h in this kind of interval notation will indicate a straight line path. Okay. So, f of zeta minus f of z. Now, what I can do is say this is f of z times h when I pull it to the numerator. Okay. So, now because I am considering a straight line path, I can include this f of z into the integration. Okay. So, this is d zeta divided by h. Okay. And now this is less than or equal to, by the estimation theorem we had earlier, this is less than or equal to 1 by the modulus of h times the integration on the straight line from z to z plus h of the modulus of f of zeta minus f of z times the modulus d zeta. Okay. So, now little f is assumed to be continuous, that is the hypothesis of this theorem. Okay. So, by continuity the integrand will be shrunk, okay, that is the idea. Okay. So, by continuity of f, okay, given any epsilon positive, okay, there is a delta positive such that whenever modulus of zeta minus z is strictly less than delta and zeta belongs to G, okay, modulus of f of zeta minus f of z is strictly less than epsilon. Okay. By continuity we can find such a delta. Okay. So, given, so if we are given any epsilon positive, okay, choose delta 1 to be the minimum of this delta and the delta naught such that the delta naught ball around z was in G. Recall delta naught is from here. Okay. So, delta naught is from here. So, pick delta 1 to be the minimum of these two, so that two things are satisfied. Okay. So, that whenever modulus of zeta minus z is strictly less than delta 1, two things are true. Modulus of f of zeta minus f of z is strictly less than epsilon, okay, and the modulus of f of z plus h minus capital F of z by h minus f of z, which we were estimating above, is less than or equal to 1 by modulus of h. Now, the integrand is strictly less than epsilon. Okay. So, I will first write this z comma z plus h integrand modulus of f of zeta minus f of z times mod d zeta. Okay, and the integrand is strictly less than epsilon. So, I have 1 by mod h modulus of h, and then the integration of on the straight line of modulus of d zeta will give me the length of the straight line, which is mod h. Okay. So, this is equal to epsilon. Okay. Since epsilon is arbitrary, so f is differentiable at every point z belongs to G. Z was arbitrary, remember, okay, and f prime of z we have also proved is equal to little f of z. Okay. So, f is analytic, okay, and then the differentiation of capital F is little f. Okay. So, that shows that f has an antiderivative, okay, and that proves 1. So, 1 is true by 3. So, 1 implies 2 and 1 implies 3 by your fundamental theorem of calculus, okay, and we showed that 2 implies 3 and we also showed that 3 implies 1. Okay. So, now we can go from 1 to 2 or 2 to 3 or 3 to 1 or any way we want. Okay. So, all these 3 statements are equivalent. Okay. So, that proves this theorem. So, this tool is useful as we will see further. Okay. So, this antiderivative theorem will be used constantly. Okay. And now, we will see another version of Cauchy's theorem. Okay. So, we showed that Cauchy's theorem is true when you consider a rectangular region. Now, we are going to show that if you can somehow fit in a rectangle with diagonally opposite ends being a fixed point z naught and some variable point z, then your Cauchy's theorem will go through. The same proof or a similar proof will go through. Okay. You essentially use the fact that Cauchy's theorem works on a rectangle and then apply it here. Okay. So, here is Cauchy's theorem, another version. So, Cauchy's theorem for a disk, let us say. Okay. So, this should be considered as a slight generalization of the earlier version of Cauchy's theorem, namely the Cauchy's theorem for a rectangle. Okay. So, if f of z is analytic, okay, in an open disk B z naught delta. Okay. So, this is an open disk centered at z naught and of radius delta. Okay. Then the contour integral of f of z dz on gamma is 0 for any closed curve, okay, for any closed contour gamma in B z naught delta. Okay. So, that is the Cauchy's theorem for a disk. Okay. And the proof of this goes as follows. Okay. And so, here is a disk centered at z naught and of radius delta. Okay. So, you consider any point z in the disk. Okay. So, it could be right above z naught and horizontally on the line on a horizontal line from z naught, does not matter, but you can put a rectangle like that. Okay. So, in the two cases that I mentioned, you will get a degenerate rectangle, but in all other cases you will get a genuine rectangle like that, does not matter. Okay. And then you consider two contours, one is this, call that sigma 1. So, you start from z naught, travel horizontally and then go up. Okay. So, it is the trace of a contour, you can parameterize that trace, okay, to get sigma 1, and then you parameterize these two, okay, and then you get sigma 2. Okay. So, sigma 1 minus sigma 2 is the boundary of a rectangular region, of course. Okay. So, by Cauchy's theorem, of course, we are assuming that f is analytic, right? F is analytic on this rectangular region. Okay. So, by Cauchy's theorem earlier version. Okay. So, for a rectangle, the integration on sigma 1 f of z dz is equal to the integration on sigma 2 f of z dz. Okay. So, so we will store this fact, we will need this fact. Okay. So, now what we do is we will define capital F of z, okay, is equal to the integration on sigma 1 of f of zeta d zeta, okay, for z belongs to B z naught delta. Okay. So, if z is any point in the disk, we define capital F of z to be the integration along this sigma 1. Okay. Sigma 1 is a fixed path. Okay. And also incidentally, this is note that this is the same as the integration on sigma 2 of f of zeta d zeta by the above note, by 1, from 1 let us say, okay, from 1. So, so now what we can observe is that f of z will decode f of z on sigma 1. Okay. So, on sigma 1, which is first horizontal and then vertical. Okay. If you consider your z naught as x naught comma y naught, okay, then your y value stays constant on the horizontal line. Okay. So, the integration along sigma 1 goes in two portions. Okay. Firstly, where you have gamma 1 f of z dz plus integration on gamma 2 f of z dz, where gamma 1 is this portion and then gamma 2 is the other portion. So, sigma 1 is actually this gamma 1 plus gamma 2. Okay. So, strictly speaking, I am talking about the traces of these paths. Okay. So, but we can parameterize them in such a way, okay, and the way we parameterize does not matter for the contour integration that we saw earlier. Okay. So, now we have split this integral into two portions. On the first portion, we note that y is constant, and on the second portion y varies. Okay. So, with that observation, I can say that if I partially differentiate capital F with respect to y, y is varying only on the second portion. Okay. So, let me first backtrack. Let me write f of z equals integration, okay, on integration from t equals x 0 to let us say x. So, I am calling this point z equals x comma y, okay, in this picture. Okay. So, then this is f of t plus I y naught, and then dz will be on the horizontal path, dz is dx plus I dy, but since y is not varying, you only have dx. Okay. And I am using the parameter t for x. So, I get a dt really here. Okay. And then plus for the second portion, I have y is varying from y naught to y, and f starts at x plus I y naught and goes until x plus I y. So, for the y part, I will use a variable t, okay, and then I have dx plus I dy is now I dt. Dx is 0, so I get I dt. Okay. So, since y is not varying on the first portion, okay, when I calculate the partial derivative of capital F with respect to y, only the second portion of this integral survives, okay, and then I get this is f of your y goes in, okay, by the fundamental theorem of calculus. Okay. So, you get f of z times I, okay, that I, there is a multiplier I. So, I get I, okay. So, which is I f of z. Okay. Likewise, since f is capital F is also equal to the integration on sigma 2 of f of z of zeta d zeta. Okay. So, f of z is integration on sigma 2, here is z equals x y, and here is z naught equals x naught comma y naught. Okay. So, by similar argument, okay, you can say that this is equal to, this is gamma 3. Let us split this into two portions, gamma 3 and gamma 4. So, the integration on sigma 2 is equal to the sum of the integrations on gamma 3 and gamma 4. Okay. So, on gamma 3 you get y is varying. So, y goes from t equals y naught to t equals y. of f of x naught plus I t, okay, times I dt, okay, plus on gamma 4 you can use a parameter t, and x goes from x naught to x of f of t plus I y, okay, y value has already reached y from y naught, okay, and then you have dx plus I dy becomes dt now. Okay. So, from this it is clear that the partial derivative of f with respect to x, okay, this representation of capital F is convenient to calculate partial of f with respect to x, okay, and the partial of f with respect to x from the second portion is clearly f of x plus I y, namely f of z, okay, because the first portion, in the first portion your integral is a constant with respect to x. Okay. So, so then you see that dou f by dou y is I times f of z, which is dou f by dou x. Okay. So, f satisfies the the Cauchy-Riemann equations, okay, and the differentiation of f, okay, it can be it can be found out either using dou f by dou x or dou f by dou y. Okay. So, sticking to dou f by dou x, we see that the differentiation of f is nothing but little f. Okay. So, and the partial derivatives, okay, partials of f are continuous. Okay. So, so by the theorem we had earlier, so f is analytic. Okay. And we conclude that okay, what do we conclude? We conclude that f has little f has, okay, f is analytic, and of course, f prime of z equals little f of z. Okay. One way to calculate f prime, remember, is just calculating dou f by dou x, right. We had 4 different formulae for computing dou f by f prime of z. Okay. So, by one form we have dou f by dou x is f prime of z equals little f of z. Okay. So, f has an antiderivative in B z naught delta, okay, and by the antiderivative theorem, therefore, okay, which we just proved, the integration of f of z dz on any closed contour is equal to 0, okay, for any closed contour gamma which lies in B z naught delta, okay, and that proves the Cauchy's theorem for a disk. So, next in order to come up with integral formulae, okay, Cauchy's integral formula, okay, which actually helps us to compute the values of an analytic function, okay, by taking its values on a circle surrounding that point, okay, or the value of an analytic function at a point by using the values on a circle surrounding that point. Okay. What we will do is we will want to define first a quantity called an index, which measures how many times, roughly speaking, how many times a curve goes around a point, okay, closed curve goes around a point. Okay. So, the intuition is that we are trying to measure given a point and a closed curve, we are trying to measure how many times this closed contour goes around that given point. Okay. So, here we will start discussing index of a point with respect to a closed curve. Okay. So, in order to define or make the correlation between how many times the curve surrounds the point, okay, and the following line integral, which I am going to state, okay, we need the following lemma. Okay. So, if a piecewise differentiable closed curve gamma, okay, does not pass through a point A, okay, then the value of the integral dz by z minus a, okay, over gamma is an integral multiple of 2 pi I. Okay. So, in short I could have said if a closed contour gamma, okay, does not pass through a point A. Okay. So, let me word it this way. Okay. Let me store this. Okay. And we want to see that this special integral, okay, actually is an integral multiple. This integral, okay, is a integral as an integer multiple of 2 pi I. Okay. So, okay, so this is to say that this is an integer, okay, is an integer multiple of 2 pi I. Okay. And that integer actually roughly speaking is the measure of the number of times the curve goes around a point. Okay. And integers have signs, of course. Okay. So, indirectly we are associating a sign. So, a curve could go around minus 2 times, for example, around a point. Okay. So, we are keeping track of the orientation of the curve as well. Okay. That is what this integer tells us. Okay. So, let us start by proving this lemma. Okay. Proof of it is as follows. Now, let alpha comma beta be the parameter interval, okay, for the path or the contour gamma. Okay. It is a closed contour, okay, and gamma of alpha is equal to gamma of beta because it is a closed contour. So, now what we will do is we will try to define h of t. So, define h of t to be the integration from alpha to t, okay, of gamma prime of t dt by gamma of t minus a. Firstly, h is defined. Before I say h prime, h is defined and continuous, okay, continuous on the closed interval alpha comma beta. Okay. That is clear from the definition. Okay. Also, h of alpha is 0, you are integrating from alpha to alpha. Okay. H of alpha is 0. So, then h prime of t, okay, is simply gamma prime of t by gamma of t minus a, okay, by the fundamental theorem of calculus. Okay. So, so this is true, of course, whenever gamma prime of t is continuous. Okay. We have a piecewise differentiable, piecewise smooth curve. Okay. So, we have to be careful, this is true only when gamma prime of t is continuous. Okay. So, now notice that if we want to find the derivative of e raised to minus h of t gamma of t minus a, okay, then we get 0. Okay. So, how is that? So, let us use differentiation or the product rule for differentiation. You get e power minus h of t times minus h prime of t, okay, the differentiation of e power minus h of t times gamma of t minus a plus e raised to minus h of t times the differentiation of gamma of t minus a is gamma prime of t. Okay. So, this gives you e raised to minus h of t, okay, times minus h prime. We just saw what h prime is, okay, and h prime is gamma prime of t by gamma of t minus a, okay, times gamma of t minus a plus e power minus h of t gamma prime of t. Okay. So, these cancel. Notice that a is never equal to gamma of t. So, these cancel and then you get this is equal to 0. Okay. So, e raised to minus h of t times gamma of t minus a is going to give you a constant, because its derivative is 0, okay, some constant c is a constant. Since it's the derivative of this function is 0, okay. So, you get a constant, and so e power or gamma of t minus a is actually a function c e raised to h of t. Okay. And so, well, c e raised to h of beta is gamma of beta minus a, okay, which is gamma of alpha minus a, because gamma of beta is equal to gamma of alpha. We are dealing with a simple closed, or rather sorry, closed contour, okay, and then that gives you c times e raised to h of alpha, okay, by definition, or by this equation here, this is your c e raised to h of alpha, okay, and h of alpha we know is 0. So, this is c e raised to 0, or this is c equal to c. Okay. That tells us that e raised to h of beta is equal to 1, and we know precisely when e raised to something is 1. Okay. So, this implies that h of beta is 2 pi I n for some integer n. Okay, and which is what we want. Okay. So, so this integration 1 by z minus a, okay, when we parameterize it, okay, we get this h of t. H of t is nothing but the parameterization of this integral, okay, and or h of beta is the parameterization of this integral, sorry, okay, and then that is an integral multiple, an integer multiple of 2 pi I. Okay. So, that shows the lemma. Okay. So, now we define this integral, okay, the value of this integral, okay, divided by 1 by 2 pi I, okay, to be the index of the point a with respect to the curve, the closed curve gamma. So, that integer we are going to call that as gamma, okay, and the intuition you will have is that you are keeping track of how many times gamma goes around a, okay, with direction in mind. Okay. So, if you have that the index is minus 2, then your curve is going around point A in the clockwise direction, okay, etc.